Okay, last lesson for Gen Chem 1. So, lesson 31, we're going to finish up some kinetic molecular theory ideas and then end on non ideal gases. Okay, so I kind of alluded to this is the direction it was going. Now, most of this comes directly from the reading. My questions come directly from it, but we're going to go through a few of them. So, what does the Maxwell-Boltzmann distribution plot allow us to determine about a gas? Well, it allows us to relate the speeds of gases to certain temperatures. Okay, so that's what it allows us to do. You can see several of these in your OpenStax textbook. Now, last time we talked about kinetic energy and velocity, so this is just a review that kinetic energy and velocity are proportional. Kinetic energy and temperature are proportional, therefore, like we've already said, velocity and temperature must also be proportional, and this would be a yes, it does agree. Now, what we already said about velocity and molar mass is that velocity increases as molar mass decreases, and this would be another yes. Okay, so these are all things we've already seen from lesson 30. So unlike solids and liquids, gases are what we call compressible. And so why does compressibility causes gases to deviate from the ideal? And that's because we reduce the space between gas molecules. So remember, one of our postulates for KMT said that the space between them was greater than the space they occupied themselves. And when we do that, the attractive forces between gas molecules are no longer insignificant. So it actually will mess up or ruin two of the postulates from the KMT theory, or the kinetic molecular theory. So what it means to be compressible is essentially we apply pressure and it reduces the volume. Okay, so we're increasing the pressure, which reduces the volume that the gas molecules have. At what two extremes, and we put this in quotes, does the ideal gas law fail to predict or explain behavior? And so essentially it's asking when are gases not ideal? And this is maybe no surprise, but at high pressures. So we just said that up here. And the other one's at very low temperatures, because you start to ruin the whole idea that the gases are always moving and they're bouncing off each other and it's random, and they start slowing down. And when you think about two things colliding off each other, kind of like slow motion, if you will, you can imagine it looks like the molecules are probably more sticky because they're moving apart slower and moving together longer. So it makes them appear to be stickier or more attractive than if they were bouncing off each other in real time. Okay. And then the last thing says, what is the van der Waals equation? Now you might panic when I write down all of these variables, because your first question is going to be, does she expect us to memorize that? And I don't. I will give this to you on the test. However, if you don't know the variables and you don't know how to solve it correctly, it's of no use to you. Okay, so I will give you the equation on the test, but I will expect you to know how to use it. All right, so that should answer your questions. Pre-lecture questions if you hadn't already filled them out. So now we're going to check for understanding of the concepts. So this says, describe what happens to the average kinetic energy of the ideal gas molecules when the conditions are changed as followed. The pressure of the gas is increased by reducing the volume at a constant temperature. Okay, so the pressure is increasing, the volume is decreasing, and the temperature is staying constant. Okay, so the average kinetic energy of all the gas molecules is going to remain constant. So what will happen when the pressure of the gas is increased by increasing the temperature? at a constant volume. Okay, so in this case, the kinetic energy is going to increase because the temperature increased. So now think about what happened up here. You may have said, well, how did she know that? Well, the temperature was constant. And if I think back to all these things we said up here, the only factor that changed it was temperature. So pressure and volume, remember V here is for velocity, not for volume, do not have an impact on the kinetic energy. So what will happen when the average velocity of the molecules is increased by a factor of 2? Well, my velocity is increasing, therefore my kinetic energy is also increasing, because temperature and velocity were two of the terms that could affect or impact kinetic energy. Next one. A 1 liter sample of carbon monoxide initially at STP is heated to a temperature of 546 degrees Celsius. So that's a pretty large temperature change, and its volume is increased to 2 liters. What effect do these changes have on the number of collisions of the molecules of the gas per unit area of the container wall? So it's looking at how does force per area, which was our pressure, okay, how does it change? So because the temperature and the volume double, but the number of moles of gas are constant, right? We're not adding any more carbon monoxide into this problem. Therefore, the number of collisions is constant. Even though we're increasing the temperature, we're giving them a larger volume. Therefore, the pressure will be constant. Okay, so think of it this way. If you guys were all walking around in 102 and I said, okay, now run, the likelihood that you might run into each other is higher if you're running. Now, if I added twice as many of you in the room 102 and said, now run around, of course you're going to hit each other more because there's more of you in that small space. However, if I took double the amount of students and gave you a room double the size, theoretically, you should hit each other less, but probably thereabouts what you would have if it was just you guys in 102. So it kind of balances out that change. What effect what is the effect on the average kinetic energy of the molecules? Well, that's pretty simple because the temperature increased, therefore the kinetic energy must increase. And then it says, what is the effect of the root mean square speed of the molecules? That's a lot of, so RMS, the root mean square speed of the molecules. Well, in this case, the temperature is going to increase, the kinetic energy is going to increase, and the RMS is going to increase, the root mean square speed of the molecules. Now, we don't spend a lot of other time talking about the root mean square speed. It doesn't usually show up on the ACS test a lot, so don't worry about spending a lot of time looking over in the textbook because it's not one of the main topics that we spend a lot of time on. But we do spend a lot of time on relating kinetic energy to temperature and velocity. So those relationships are very important. They will show up on exam 4 and they will show up on the ACS final. All right, a few more. So the next one says, under which of the following sets of conditions does a real gas behave most like an ideal gas? Okay, so real gases are just another way of saying something that is not ideal. Right? We have ideal gas. We say that this is likely to be the behavior in theory, but very few things actually behave like that in theory. And so real gases are what we really see. They're actually what we observe. And for which conditions is a real gas expected to deviate from ideal behavior, and explain? Okay. So we already kind of answered about the deviation from ideal behavior. So we saw that we said high pressures and low temperatures, that we would expect the deviation. So we see high pressures, low temperatures. So this is where we would expect real gases to deviate from ideal. Okay, we increase the pressure, we increase the temperature. We're talking about the volume being significantly less, the space between the molecules, the sticky collisions, all of that kind of takes over. So then the first one says, under which of the following conditions does a real gas behave most like an ideal gas? And it's the opposite. At very high temperatures and very low pressures, real gases tend to behave most like an ideal gas. Okay, so it's just the opposites, and then this is not anything. Okay, the reason why is at high temperature, we are now minimizing the attractive forces. They are like ping pong balls bouncing around, or like 3-year-olds you've just given 5 cupcakes to a piece. Okay, they're moving around with high velocity, therefore their attractive forces are minimized. And because the pressure is low, we are not reducing the volume. Oops, let me try to make that look. Not reducing the volume or space between the molecules. Okay. All right. So this was for the B, and this answered the first part of the question. All right, now to the math. You will see a question like this on exam 4. It'll look almost just like this. So be prepared to recreate this. Now, I've already told you I don't expect you to memorize the van der Waals equation, so you will not panic. It will be there on the test, written in where you need it. However, the ideal gas law equation you will need to know. Okay. So short answer, guarantee. Remember, I told you guys that I don't write the test before I do the lectures, but I write the, well, I don't know if I've told you that, but I write the exams as we go. So mentally, every time I see a question, I'm like, oh, I usually like to ask that one. And this is one I like to ask. All right, so we have a 0.245 liter flask containing 0.467 moles of carbon dioxide at a temperature of 159 Celsius, and we want to calculate the pressure. And we're going to do it 2 different ways. We're going to do it one way using Pivnert. So let's go ahead and start plugging those values in. We are, it doesn't tell us what to specify the units of pressure in, but I like to use the ideal gas constant that's a 0.08206. All right, thank you, Anderson. Okay, hopefully this is the last interruption for the semester. He wanted to tell me he knew where something at Walmart was. We're already making our Christmas list, and it's September. Anyways, okay, so back to the problem. I do need to convert my Celsius to Kelvin. Okay, so go ahead and do that and plug it in, and then I'm going to divide by my volume. Okay, so it's really nice when everything's kind of ready to go. All right, so now we're going to take 0.467 times the ideal gas constant times the temperature and divide it by the volume. And we should get 67.6 atm. Okay, that's the pressure we calculate of an ideal gas, carbon dioxide, at the given variables of pressure and temperature, of volume and temperature. So now we're going to do the same thing using the van der Waals equation. The nice thing about the van der Waals equation is it is already solved for pressure. It's kind of a gnarly equation if we have to start rearranging it to solve for something else, okay? So I would ask you on a test to solve for pressure because I don't want you to make any sort of mistake on rearranging. Dr. Spencer, if he's in there with you today and you are a chemistry major and you make it to PChem, he may ask you to solve for another variable, but not today, okay? So we need to know a few things. The first thing we need to know is what A and B are, and the nice things is that A and B are constants. They are not constants that I expect you to memorize. One is a correction for the molecular attraction, and the other one is a correction for the volume. Okay, so they are not values to memorize. They are values that you would be given in a table, and the values are specific to the gases that you're working with. So like carbon dioxide has its own values. So in fact, let's go ahead and go over to OpenStax, and I can show you what I'm talking about. Telling you I am this battery and I. Okay, so here are your constants for some common gases. Okay, so you'll see the ones that we're going to use are 3.59 and 0.0427. Okay, so these are experimentally determined, but they are constants. So you'll see here the correction to pressure in the terms of ideal gas law comes in the n squared A divided by volume squared, and the correction to the volume is the n minus b. Okay, so they're corrections to our Pivnert equation, and they are constants you do not need to memorize. So now that we have our terms, make sure I get them right down, 3.59, and we may not have paid attention to the units. I know I just left that slide quite quick, or that thing quite quickly, so let's go back and look at them. Liters squared times atmospheres divided by moles squared, and then B is liters over moles, so it's the opposite of molarity. Okay, and the nice thing is that as long as you're needing to solve for pressure and atmospheres, then these constants don't need to be converted or changed in any way. You can just plug them in and all the units should cancel out. So now we just plug and chug. This will be the last time you hear me say that for the fall semester. All right, and then we have our temperature. We're going to divide that all by the volume and its correction, which is the number of moles times B. So you can see here where the moles being on the bottom are going to cancel out, and then I got a little sloppy. The liters in our volume terms will be able to subtract. And then we're going to subtract from that the whole other part. Times A. Oops. Seems like a lot. But the nice thing is if you write it out carefully the first time, you should not have to do it again. All right, so moles, moles, Kelvin, Kelvin. Then it'll be moles and moles, liters and liters and liters, which would leave me with atmospheres on top. And then moles squared, liter squared, liter squared. So it'll be atmospheres minus atmospheres. Now, the trick here is not to make a math mistake. So if you want to type it all into your calculator, you can. I don't like to do that on these problems because it's really easy to make a mistake. So I do it step by step. Okay, so I solve for the top part. Oh, buddy, get away. Now the cat's after me. I multiplied those together, and now I'm going to do 0.467 squared times 3.59. And remember, I'm just leaving enough digits to hopefully not mess myself up in the end by rounding too soon. Alright, so almost there. So if I take 0.245 and subtract it from the value I got from n times b, if you're really confident with your calculator and you plug this all in, I am very impressed. And I wish I had those skills. Okay, so this will be 73.558 minus 13.0418. And now the last step is to subtract. And I did pretty good because my number matches my lecture notes. And that's that the pressure, according to van der Waals, which is the non-ideal gas equation, is that it is 60.5 atm. So we can see that they're still close. The numbers are not, 67 versus 13. It's 67 versus 60, so they're in the same ballpark. And it says explain the reason for the difference, and that reason is the intermolecular attraction and the volume. So if we look at our values, you can see that we're at a very low volume, 0.247, and these are actually pretty high pressures, right? And the temperature is also 432, 159 degrees Celsius. Okay, so the reason for the difference is the correction for the intermolecular attraction because of the reduced volume, and which we explained here. Sorry, I ran out of space. Okay, so this will complete your lesson notes. What will happen next class is you will have an opportunity for review and asking last minute questions. I shouldn't say last minute questions, but touching base with Dr. Spencer or Dr. Morris over any concerns, anything that's come up, because you will have a quiz that's over the last two lessons. So that's lesson 30 and 31. And then your exam 4 will be, so this should be Monday, today you're watching this, and then your exam will be Friday. And then your final exam, just to make sure you know, is Wednesday, December 4th, 8 to 9:50 a.m. It is a standardized test, and so you are given an allotted amount of time. It's 110 minutes. You do not need to bring anything with you except for a calculator and something to write with. You will have a test booklet with scratch paper in it and a Scantron provided, and you are not to write in the exam at all. These are not copies that we purchase every year. These are things we keep for a while, and we hope not to have to buy more. So if you write in them, then we cannot use them again because they are written in. Okay, so you do not need a Scantron. You only need your calculator, and that should be it. Okay, I'm going to ask that Dr. Spencer or Dr. Morris, whoever proctors the final and exam 4, will keep up with my rule that it's an exam for a phone. So you need to turn in your phone to get an exam when you take exam 4 and the ACS final. Okay, so if you don't bring your phone, you will not have an exam to swap. Okay, so make sure we don't change anything that's happening just because I'm not there. Good luck studying for your ACS final as well as your exam 4. You need to try really hard on the ACS final, my rule is if you get in the 90th percentile, which is an A, you automatically get an A in the course. Okay, so if you have a C and you get into the 90th percentile in the ACS exam, you earn an A in the class. It's not impossible to do, it is difficult to do, but it is not impossible. Okay, you need to study very hard for that test, and I wish you all the best of luck, and have a Merry Christmas and a Happy New Year, and I hope to see all of you in the spring. Please email me if you have any questions or concerns that you don't feel you can get addressed with Dr. Spencer or Dr. Morris, but I think that you should be able to have everything addressed with them there. Okay, bye.